Okay. So I will kind of talk a little bit. Oops. Why I can. Okay. Let me pull the chat down here. So I will continue our discussion on CNN, and then in particular, we will talk about some applications on CNN. Um, that would be like a repetition of like a little bit of like what Vishnu has presented, like on the, for example, like our CNN and so on. But yeah, hopefully it's okay. Like it's not too much repetition. So so we like to look at okay some applications like CNN. Most um, kind of at least initially most of the applications are on computer vision, on image processing and so on. Um, so let's look at like several of these applications. Um, that's on computer vision. Like besides like just image recognition, so we'll look into like semantic segmentation, like object localization, detection, and so on. So so far like we talk about like several different network models. If you remember, like uh like just like plain like vanilla like CNN, basically more or less like Alex like the simplest architecture. And then we briefly mentioned the VGGNet and ResNet and also like Google Net with the inception module. And so and all of this like we benchmark that with like image classification. So that basically given an image, we're just trying to say like what kind of image is that? Like we have different classes. So look at the image and then determine okay, it's a cat. So for classification and localization is a little bit more challenging. So besides just like trying to okay, actually here is showing like all four kind of like different applications we want to look into. So so we have like semantic segmentation, like localization, detection, and so on, also instance segmentation. So I guess we start with like semantic segmentation. Yeah, semantic segmentation. So it's basically it's just that you have the entire image. You want to classify for each pixel to determine whether like what kind of pixel is that. Like in this like very nice example here. So for this, all this pixel here is basically correspond to grass, and then here is the cat, and then there's the sky, and then there's the trees, and like that. Um, so for semantic segmentation, like we really can build a. If you think of using CNN, you can just think of like for each of the patch, trying to classify what's the value of the patch, right? So we can just have like multiple layers of CNN, and then ultimately, we'll have output for each of the pixel. Um, say okay, maybe like this. So we have like layers of convolutions, and I guess like I may need to. So we have layer convolutions, and then near the end, let's say I have another convolution, but basically have like more let's say the number of filters would be like let's say if I have like C classes, then the last layer I will have like C filters there, each filter corresponding to like corresponds to different class, and then like we can just take the softmax of all these classes. So per pixel, like for these C classes, or yeah, or we don't even need to do softmax. Maybe we just if we don't care about the probability, we can just say look at which one has the highest score there, and then high score will be correspond to the class that we believe it belongs to, that pixel belongs to. Um, and this is a very simple model. The problem is I just we have quite a lot of computation this way. Like for each of the layer, if we do the convolution over the entire image. So typically we want to do some downsampling. So if we do some downsampling, as like what we do, like for example in classification, so once we go downsampling, in this case we need to go upsampling again, right? Because the output now have the resolution of the entire image, right? So if we do semantic segmentation, unlike we do a classification, the output will just be one value, right? But here, like we will have the output is like have the dimension like the same as the input, or like yeah, more or less the same as the input if we don't count the color here. So now the problem is how to do upsampling here. So for think of like a CNN, like what kind of um, operation like we have like in the CNN, what kind of computation we have. So we have of course the conv layer doing just convolutional filter. Maybe I put this over here. Like we have like conv filter here, right? From the convolution, like, and then we have sometimes some pooling, right? Mass pooling or like even FH pooling, and then like uh we have activation, right? So maybe value and so on. So out of these three different operations, like activation, I don't care about that because it doesn't change the dimension, right? So if like the original dimension, original size is like h by w, after activation, will be, basically the dimension will be exactly the same as previous layer. So then we don't need to worry about that. Only this two is going to have like downsampling, right? For convolution, like if strike is equal to one, there will be no downsampling. But if strike is equal to two or like anything bigger than one, then there will be some downsampling. Then I will get smaller. Then I need to upsample again later on. And pooling, like often also like the strike typically will be bigger than one as well. That will be we need to kind of like figure a way for upsampling. So so first like think of like pooling, like how do we do unpooling? So there's several candidates here. Let's say if I start with like this is I start with 4 by 4 and I have some values here. Let's say 0, 1, 0, 0, and then 2, 1, 1, 1, and then like 3, 1, 2, 3, and then 1, 2, 3, 4, let's say. Now, when I do pooling here, do mass pooling, then I get 1, 2, 3, 4 here, like the maximum of this. Now, when I this is a part that like in the earlier part that do downsampling. When I and the later part when I need to upsample the dimension again, then one way we can do is I simply do the nearest labor. So if this is one here, we'll propagate, or like I should say like it's like a zero order filter. I will just like multiply this or like oh, okay, or like simply like for all file values here, I will set to the value here. That's one possibility to do that. And other possibility, maybe I can do this kind of like bed of nails. So it would be like I only for like for example like okay actually I here I didn't do the values that is beside maybe I just oh yeah the bed of nails I would just say take only one of them as uh to set to non-zero and for the rest we just set to zero when I upsample that and I can also do like this so-called mass unpooling. So, okay, this give an example here. So I will only basically for the, when I do pooling, of course, only one of the values actually contribute to the actual output, right? For example, if I have, this is the input here, when I do pooling here, actually only this guy, like this is highlight, okay, anyone, and of, I mean, the one that is highlight with colors are actually contribute to the output, right? So let's say this one is the mass one is 5 and this one is 6 and so on, right? And then this one. So when I do backpop, I shouldn't say backpop. When I go back up here, let's say here I do the downsampling. do the pooling here to get downsample by one half. When the corresponding layer that to do upsampling, I'll just propagate this information to here. I'm saying that, okay, since earlier, this guy contribute to the actual output, I will only like have this guy kind of get the value here, like when I upsample. For the rest, I will simply set to 0. So this is mass unpooling. And and we mentioned, okay, like besides pooling, like the other operation we need to take care of is a convolution, right? So if I of course, if yeah, actually, even though your stride is 1, you may still like think of like how do you do the uh, inverse convolution. But typically, the reasonable way to do that is simply like multiply by the transpose. Like, what I mean is like if you in the earlier layer, let's say again, like if I have an earlier layer that have I need to move this thing away. Uh, uh, you cannot see it, but like basically the zoom thing is like, oh, okay, can I? That's very annoying. How can I? Okay, okay. So so let's say in the early layer, I have some input here. Let's say I have some input, a particular layer here. Maybe I zoom in here. Just somewhere here. I have an input x that multiplied by, let's say I have the output is y, is x multiplied by a convolution kind of like kind of filter like represented by a matrix W. So and then like if I at the very at the other end, when I want to do the inverse operation, not exactly inverse, I can just say do a transpose. So let's say if I up to here, I have maybe I call it y tilde or like y pi, and then in the next layer, let's say x pi. So I have like x pi. I can use a W transform multiplied by y pi. Let's say. So um it is not exactly the inverse, but it's not does not have like lots of like I would say like it seems like it's a reasonable way to do or like the most reasonable way to do uh for given that like you only have information of W, like what else you can do by the way. Yeah. So this give an example here. So if I in the forward here, let's see. Oh, actually maybe I look at I just one the example first. So so here, like, let's say I have the filter, like that's the filter that um was trained earlier or like in the earlier layer that basically the W we have like earlier. So when I'm doing forward, like what we use for this filter will be like, let's say if I have let me just maybe I put some concrete number, or maybe I just make it even a question here. Let's say I have like layer 1, 2, 3, 4, 5. That's the input. Let's say now I have a filter of like 1, 2, 1. Let's say. Uh, so now this is just an input, just a question about convolution. So if I do low padding and strike true, what was the output for that? Like this is the input. Let's say this is the input. This is the filter. This is not transpose convolution yet, but this is just simply like regular. Okay, I'm not sure you can read my. This is 1 to 1 here. Something very simple. Oh, be careful, we have no padding. The question is, I have input is this one. It's just doing a convolution. So I have the filter. So you have a conv layer. You can feel I have a conv layer here. And this is my filter here. Let's say this is my W here. And then I have input X. Then what is this output here? I'm assuming for this layer, I have no padding. I'm strike 2. Yes, yeah, it's quite simple. Right? So I have no padding. So this is the first one I can do. Right? So 1 to 1 dot product with this guy. So it should get 8. And then I move strike 2. I should move like 2 coefficients I had. So like it will be here. So I'm then like this part like dot product with this guy. So whatever. So okay, this is a doing going forward. Now if I continue to go, like if you say I have some kind of telescope, this kind of structure, right? So I have like one layer that have this filter is like 1 to 1 here. Uh, I'm going to use the same filter when I upsample that, but I will use the kind of multiply by the transpose instead. So as you can see, it will be like example like that. If I have two values, these two values here. Now I have this filter is like this guy here. So I'm going to expand that to to be like this, right? So it's like essentially it's just like this one, basically this part here uh, will be scaled, or like I should say this filter here will be scaled by the A, and then we will put in here, right? And that's basically the original location that you're supposed to do dot product with this guy, right? And similarly, like for this part here, for okay, similarly for the filter also like will be kind of scaled by B here and put into here, right? And then I will just add all of them together. So I make sure you understand what's going on here. I know I'm not really a kind of very articulate person. So give the, this exact example here. Now I have this layer. I continue to go away. So I have this output here somewhere is a uh, you say A16. Okay, let's say like after several layers, let's say like then the output up to here, I have the input is like maybe just 2 and 3. So let's say, so what should be the output here now? Or I should say like when I have input 2 and 3 and go for a transpose convolution, filter 1 to 1, what will be the output? Again, I will match the condition that I have earlier on. So in the earlier layer, so therefore it will also be like low padding and stride will be 2. So input is 2 and 3. Another question here. Yeah, different has answer. So it's yeah, yeah, okay. Yes, yeah, yeah, it's actually quite simple. Like if you understand what's going on. So okay, I guess you kind of get that. So okay, let's try a 2D example, like maybe something similar here. So I don't know, maybe this one here. Let's see. Huh, okay, this. Mm, actually, this figure is bad. Like it's kind of like misleading. Like I say, like let me use somewhere here. Let's say. So just make sure. Like let's do a simple 2D example. Also, like let's make a question here. So let's say I have input now. Same thing. So 1 1 2 0. Let's say, and I have the filter is 1 1 1 1. Let's say something like that. So so this is the input, this is the filter. Uh, so it's again I'm going to have a transpose convolution. Um, so I have this input, this filter coming in. So and the filter also like again like let's say low padding and then strike this two, let's say. So what would be the output? So is the question here? It's just say from 1D now become 2D. Filter. Oops, I cannot spell filter. Uh, okay, it's 3 by 3 here. I just didn't write the zeros. Yeah, it's something like this. Ah, oh, by the way, like after this question, I guess we should kind of like uh talk about the midterm first. We need to resolve this logistic thing. Um, uh, oh, we are not, okay. This is doing transpose convolution. Know that like you can think of like something like a inverse convolution. So it's like doing upsampling with convolution here. So normally, if you do convolution with a stride two or like stride larger than one, you will get downsampling, right? So when you do transpose convolution, like, it will be opposite. When you have like stride larger than one, then you will have upsampling instead of downsampling. Uh, oh, okay. So it's okay. Let me go through another example, then maybe come back to this question. So let's say I had to something similar. Uh, Now one let's say 1011, let's say this is a input is this one, and then let's say the filter is 1221, let's say. And now I let's say I've tried strike two or strike two or yeah, let's try two. Or maybe just try one and I get no pattern, let's say. So then what will be the output here will be you can think of like I have one multiplied by this filter, I get 1221 here. Maybe how do I write it better? Maybe I use several different color. Let's say 1221 here. And then for this one here, that with no contribution, but I will be like for this guy, should be this. Maybe I use this color for. I will be like okay, I'll be like 0 0 plus 0 plus 0 0 0. So basically, like I I I have the filter itself is kind of scaled by the coefficients here, and then like they are shifted by the corresponding like location of this coefficient multiplied by the stride. So since it's stride one, then it's like just shifted by one here. So like this guy have one originally I filter 1221, I have 1221 here. And for this guy, like 0 multiplied by this guy is just all 0, right? But it's shifted by this one here. And then when I consider this one, then I will have like 1221 again, but it's shifted down here. So I have 1221 should be here. 1221. So does it make sense? And then for the last one here, let's say this one will be again 1221, but it will be shifted like by horizontally, both horizontally vertically by one. So I have like this one plus two plus 2 plus 1, something like that. So therefore, like the output will be like this will be 1 2 0 3 4 2 2 3 1, something like that. So maybe I also give an example of strike 2 here. So if this is strike 2, where should I put that? Maybe here. If I have strike 2 here instead of strike 1, let's say if it's strike 2, then I will have, yeah, actually basically will be very simple because then I first say if I consider the first one is like 1 2 2 1 here, and then this guy here, sorry, this one here will be shifted by 2. So therefore I will have say something like 0 0 0 0 here. And this one will be like the green one will be shifted down like vertically by 2 because it's strike 2. So it's like 1 2 2 1. And similarly the last one also 2 2 1. So therefore when strike is equal to 2, the output will be simply this one. Is that clear? Yeah. So now we can you can go back to these questions are the original question now. So if input is this guy and filter is this guy and strike is 2, no padding. So what would be the output? Okay. Okay. So we have an answer. So yeah, it looks probably correct. I don't know. I think yeah, it looks right. Yeah, I think you guys probably is right. So I didn't check. So okay, it looks like you guys are right. So by the way, like what is like if like if my padding is equal to 1, do you know like what should I what will be the value instead? Uh yeah. Yes, you need to be remembered that like if you should shift it by strike multiply. Okay, yeah, should be shifted by the uh by the offset in the input multiplied by the strike. Yeah. So if padding equal to 1, uh so know that like if I padding equal to, so think of this as like a inverse operation, right? So of the original convolution, right? If we have the original convolution, padding is like at the beginning of the operation, right? So therefore, like if you think of like this is the kind of the inverse operation of convolution, padding should be applied at the end of the operation. So basically, if you have the padding is equal to, I'm also like the opposite of like padding by one, like opposite of like padding by one would be just removing uh, kind of the boundary by one, right? So therefore, like if I have like padding is equal to one, then I should have like I think your output is what like maybe I write down the output first. The original output like padding is equal to zero is something like that. I guess like 1 0 1 0 1 0 0 and 1 0 3 0 1 0 2 2 2 3 1 2 1 something like that, right? So if if my padding now is one, then it means that I need to remove the boundary by one, like on each side. So I should remove this boundary here, boundary here, boundary here, boundary here, here, so that it should get you just this part, like this 3 by 3 matrix here, if pattern is equal to one. So okay, so make sure you know this kind of stuff. So okay, like before I continue, I guess we will need to talk about the logistic, like for I don't want you to see the message here, but I guess we didn't have a really uh kind of like um but just a quick scan of this 413 probably is the best time for like everyone almost. But Marin only have like this one is 420 is okay, but like some file 420 is okay. So so if I just do a majority vote here, like if taking the task like or like the midterm like for 13, so anyone really have a reason that like cannot do it like somehow um so everyone is here. I see everyone is here, but everyone really is here. Here is here. Uh, so I guess I will take 413 then. Like 413. This is a what? 2 weeks from now, basically. So as I mentioned, uh, I will put the task on Canvas, like make it just an assignment, and the link will be available like for the class time to get started, and then like it won't be a very long task. Basically, I guess you should be able to finish it 1.5 hour easily. Uh, of course, you need to know the materials. For example, like if you don't know the stuff, and at that time you're trying to figure out what's going on, then of course you won't have enough time. You won't have enough time even for a day. So, assuming you know the stuff, and it's quite simple questions, I would say you can get it done in half an hour or something like. So so it should be enough time for you to uh I don't know whether you guys have something to do after the test, but let's say uh yeah, around 6, I guess I will set the deadline for 6. Then you guys should kind of like scan, take a copy, or like just take a photo and then send it back, like I mean submit it through Canvas like by 6. um so okay, like we decided okay for April 13 then. um that's the logistic for the test. So I would say like the test is quite simple. So if we have all these like participation questions, if you are able to know what you're answering, then most likely you're doing fine with the test. Yeah. So if when you go through this all these like participation questions and you find that you don't have any problem at all, most likely you're doing fine. Otherwise, you may want to go back and revise um, some of these materials. So okay, and so let's continue and. Well, yes, we are talking about semantic segmentation, and the reasons to talk about transport convolution again is like we have this downsampling, like because of the pooling, and just because we want to get lower complexity somehow, and then we do upsampling again. So to do upsampling, we have to do this unpooling, and for the conv layer, typically we'll do a transpose convolution. Um, and this is a kind of an example like, oh, by the way, like I guess I mentioned earlier that like people like to talk about FCN like in the literature and like in this community, like it can be kind of confusing like to people just get into the area recently because it sounds like it would be like fully connected network, but really most people are referring to fully convolutional network. That's basically trying to remove the fully connected layer in the network. Um, and one reason I actually at least two reasons. One is that fully connected layer is expensive. Computational wise, there are lots of parameters. Actually, then there would be three reasons. One is like the fully connected layer have lots of parameters. Secondly, like the fully connected layer will be kind of computationally heavy because you have lots of parameter basically. And also like when you have a fully connected layer, you're kind of stuck with the dimension basically. So let's say if let at the very end, just think of AlexNet or any network, they have a fully connected layer here. The fully connected layer, like you need to predetermine like the dimension of both input and output, right? The output, like if you have like 100 classes, okay, I know that will be 100 classes, the output will be like 100, I say. And here, like the dimension here will depends on the dimension of input, right? Let's say if you have the original dimension 128 by 128, and then let's say you did downsampling twice, maybe a simple letters, or like maybe three times, then you each time downsample by two, so it will be like 128 over 8. So it will be like 32 by 32, maybe at this point here. And then the fully connected layer will be like 32 by 32. So that the dimension here will be like 1024, I guess. And and with the output is like 100, let's say. So we will have dimension like this, right? And we'll be like stuck in the sense that I cannot change that. For example, like if I want to change this to 256 by 256, then this dimension here will be different, right? So therefore, like this, of course, you can retrain this layer here, but basically I cannot just use this network directly. Of course, you can resize the image also, like typically what people do is simply resize the image. But on the other hand, if you don't have the fully connected layer here, you don't really have this restriction on the dimension of your input. Yeah. So anyway, uh, this is just a semantic segmentation result like using this kind of fully convolution network. And to talk about this semantic segmentation, I should really mention the UNet. This is a introduced in the medical community for segmentation as well. And it's pretty much a very similar idea as you can see like in this piecewise network here. You also like have like downsampling and the upsampling. The major difference here is like you see that when they do upsampling, they also add a piece of the earlier output, like from the earlier layers to this one here, just cascade into the input. So basically, I take this part here and put it here, and then as the input, together with the upsample inputs, and to continue to pass through the conf layer. And similarly for this layer as well. So when I upsample this guy here, I also like pass a piece of this one here and attach into here, concatenate into here, and then uh, the combined concatenated tensor will be passed into the next convolutional layer, and so on and so forth. Like, so if I don't have this branch, then this is essentially the same as like the previous network. So, and this is some of this result of UNet, like it's doing quite well for semantic segmentation. Um, Now let's talk about classification and localization. Earlier, of course, we only talk about classification. Now, if I also like want to localize, so that basically trying to find where's the cat precisely, then one simple way to do this is, okay, basically the difference, by the way, of this thing, localization problem, and also the object detection problem is that like in the localization, when we say like object localization, typically we only assume there's only one object here. But for the detection problem, we assume that can be like multiple objects. So for the localization, since we only have one object, right? So a very simple solution will be just like after we classify the object there, we also try to kind of as kind of construct another lateral, just basically feed some of the output from the earlier lateral layer into this another branch, and this layer will just do a regression. So we have a part to classification with another branch to do regression, and the regression will try to find exactly where's the box localized. So therefore, it's a pretty simple. So then we can train like the entire lateral, like end to end, right? So we have two laws here. So at the same time, we basically we sum these two laws together, right? Weighted sum these two losses. One loss is from the classification loss. The other one is from the regression loss. And of course, we can do something like beyond localization. For example, like we can do like post estimation, because like you can think of the location of the joint is also just a regression problem, right? So instead of like if you try to localize, then if you put a bounding box, you have four numbers here. You need to determine the width and height of the box and the center of the box. If I want to do a post estimation, then I need to localize all the joints. So for example, for a person here, I can kind of assign like 14 joint positions, and each of them have like XY coordinate, and I have like 28 values to regress. So yeah, this is just repeating what I said. So now for object detection, this is the one that like we should like talk about. So I just quite quickly went through that. So for detection, it's a more challenging problem, as I said, like than localization, because you don't know how many objects in the scene you have. Uh, so therefore, like, you cannot ahead of time, for example, do the same trick of as localization. Because I may have like only one object, one cat here, but I have like a couple animals here, and or maybe I have lots of duckling here. So then the way to do that, like, okay, the simplest, the most naive way is I can do a window, a sliding window. Basically, we slide the windows for each of these, and then I determine whether there's an object or not. So if there's an object, then we try to kind of say it's an object, also try to kind of use regression to find the location, precise location of the window. So the problem here is that this is very computationally intensive, and moreover, like you can think of like it's not just like one box can fit all, because you may have like some animal is bigger, or like they are kind of like closer to the camera, so it appear to be bigger, and maybe some of them are smaller, like they're farther away from the camera. So then you need to like take care of like trying to like also do a sliding window of different size as well. So therefore like really expensive. So initially like there's a pretty early work now because I uh this neural network thing is like kind of like accelerate like a rocket. So this is a back in the date, I guess, let's see. Some of the work say in 2014. So the idea is like not really deep learning, but it's like people in computation like have already like studied for many years to generate something known as a region proposal. So basically look into a scene and decide like which part is interesting. So they already generate this kind of like windows here, determine, okay, most likely here there's something interesting. I don't know what it is, but something interesting. Here is also something interesting, and so on and so forth. So then instead of like going have a sliding window have like a million of different combinations. So we first have like a region proposal algorithms. It's classic algorithm that will spit out, let's say, like 1,000 different region proposals. And then from each of these region proposals, we are trying to see if there's an object of interest, and then also trying to regress the exact location of that object. This basically uh, that lead to something known as RCNN. Now it's back to like 2014. So it's exactly what I said. Like we have some kind of region proposal, then like for each of them, like we rescale that and go for a complet, and then trying to uh, kind of do SVM and regress and so on and so forth. The problem is like this thing is like it's very difficult to train end to end, uh, and so it's very expensive. So almost immediately, okay, there's a faster. Also, there's a SPP net, but yeah, I'm not going to talk about that. So for fast LCN, that's basically from the same authors, and I introduced the next year trying to address this kind of problem. So they found that like many of these computations can be kind of like they are repeating many of their operations. You see, like because when you do convolution here, so um, for each of the vision proposal, we compute the convolution again. So this is kind of very expensive. If we have 1,000 uh, kind of, kind of vision proposal, then we need to compute this conflict like 1,000 times. So instead, what they did in the fast RCNN is say we just do conflict once, but again, if we have some region proposal. So when we have the region proposal, we're trying to figure out like which part like in the conflict coefficients correspond to the region, and then like starting from there, we plug in this guy here like as before like to uh to do like the remaining layer trying to do detection and sorry to do the classification and also the regression. Um, so this is like much faster with like removing like most of the computation, or like we share most of the computation with only one conf layer. So it become much faster compared with like the original RCNN. So training time is faster and testing time is much faster as well. So the original RCNN is like this 49 seconds to test. So for one image, so definitely not real time. Uh, but for fast RCNN, if we exclude the computation of the region proposals, it's only takes 0.32 seconds. But now then if we look at that, compare with the time we spend in the actual network, the computation of the region proposal become quite expensive. So to fix that, that is the trick that people use like often. It's like, okay, we have this classical algorithm is expensive. Let's train a network to replace that, and the network usually will run much faster. So that's exactly what faster RCN does. So basically, like instead of like using a old classic like region proposal algorithms, it just train a region proposal networks, and the network can run much faster, and the region proposal network um, will be trained along. So in the way like here, because this guy here is not coming out of like something else like outside the network. So it'll be like this coefficient can be trained also. So therefore, like it's even easier to train end to end. So you don't have like this part like the input is like plug in like from some uh legacy like algorithm to extract the proposal. Um, so anyway, so this is an extra benefit, and also like, it's much faster. So that the turn out the speed will be like just like 0.2 seconds. This is test time. Like, of course, it's still not quite real time. If you think of like real time, you want to have like say 20 frames per second, so you're looking at like 50 millisecond to one. So it's like here is like 0.2 seconds still, but it's like still doing already quite good in terms of speed. So one work I want to mention, this is a work like after like faster our CNN, basically from okay, I shouldn't say from the same authors, but uh coming her like he was in many of this earlier paper, was also in this paper here. So the regions, okay, the region space epsilon, like as we mentioned earlier, like this is just doing the fully convolutional network. And the thing that is kind of the lawful main lawfulty here is that like we have, let's see, we still have this region proposal here. And so maybe this next slide is better to explain. So here, like I have uh, when I pull from a region proposal, or like I've okay, let's say that's part of the image I'm interested in. So when I pull from this image, I will kind of like consider like different location of the image separately. So let's say here, let's say if I have k is equal to 3 here, this is exactly illustrating k is equal to 3. So I will be pulling like I'm not sure I should say pulling. I will, yeah, actually they call it pooling. They call it selective pooling. So I have like uh let's say this region, each of these 9 different regions will be passed to the lateral separately. And then like each of them will correspond to uh a different output. So therefore you see that like each of them, like if I pull that separately, I have like um 9 times like this k square is basically 9 times like the number of classes plus one. Okay, plus one is like the background basically. So assuming I have like C classes, and I have another score is like for the background class. So basically it's not it's nothing. So then I let's see. Yeah, I have, so therefore I have 9 times C plus one score, C plus one scores here. Um, then we will just like rearrange back. So or we rearrange that back to uh this shape here. So well okay, I'm sorry, like I guess I'm kind of probably like confusing you guys. So here, like when I pull it like separately, right? But like each of them like will go for a different layer. So therefore, like this is a here like for different layers is a top left layer, like the top center layer, and this bottom right layer, like these different layers. After this, I can rearrange back, rearrange them back into like this k by c plus one. Um, and then like each of them will be correspond to a different score now. So I can do a voting now to determine like whether this is a good or bad. The voting will be simply add them together. So this will be an example. So let's say if I have baby here, so what I mean is like for uh the k square classes, in this case, or I shouldn't say class, k square region, subregion here. So the let's say I have this top left and top center and so on, different regions. And this correspond to like this is showing is uh, when, let's see. Oh, yeah. This each of this is correspond to different layers here. So, and this is saying that like if you have an object here, um, for yeah, if I have object here, so then the top left corner will be at here, right? And then like I will have like high activation if like I have an object here. So if I have object here, I have like this guy here should have high activation. As you can see, like this is exactly the case here. So I have the baby is right here. So then uh this is saying that like okay, I sounds like very probably like very confusing. I'm sorry about that. So um but anyway, like so the school each of this guy, so what I want to say is like each of this guy uh, is doing separate job in saying that like this is just focus on this corner, something like so something like if you have a baby here, for this corner here is like highly activated. Uh, so therefore I will just pull back like on this corner here. So on this of different box here. So for example, like this one now I should pull in here. So that this is a mostly white, but there's some dark here. So therefore in this color, and for this one is a mostly white here, and so on and so forth. So afterward, like I can do a voting here. Like I vote all of them together, basically, like just sum them together, and then like uh here I will have a high activation. Therefore, like, the baby is here. So on the other hand, if I have example, if I shift it like this one, so then like uh for this here, this correspond to this corner here. So if the baby is right here, it's saying that like the probability that like your um the top left corner uh is this region here uh it's not okay, at least it's not as likely as this one here. So therefore you have like a smaller activation and so on and so forth. Like when you add them all together, then you have a worse activation. Therefore like it is able to detect, okay, the baby is not here, but baby is like here in the previous slide. uh, so maybe also like just mention like something known as the feature pyramid network. It's essentially like incorporating like all of this idea, but just adding like um one more. I mean, like it's very much like the UNet thing that you have this uh up sample, like when you go down and then to go up. So it's essentially actually I think it's very much similar to UNet, but the difference is like for the UNet, in the core lateral you usually just have the conf layer there, but here's the core lateral is actually using a Westlet. So but you have the feature uh so Wait a sec. Okay. Another thing here is in I cannot recall like whether UNet have that. So, but maybe someone modified that have that. Like, it won't be too surprising. For this one here, like, uh, since you are doing like upsample, downsample and then upsampling, right? So when you downsample and upsample, you actually have like different scale or different scaling version of the image. So at each scale, you can really like do a prediction as well. So and that's and therefore like it gives you like already like multi-scale um detection. Like that's something like addressing like the earlier issues I mentioned, that like if you have multiple object, like some object is like farther away, or some is like closer. Yeah, if you use the this pyramid network here, so then like you are basically you can um detect objects at different scale. So okay, I guess we near the end of talking about this object detection, but I would like to mention YOLO, of course. Um, the earlier kind of like methods I mentioned, like all of them are basically two stage um, solution. So we will first like find a region proposal and then trying to detect the object. So YOLO is trying to just like only look at the image once, or like there's another version like SSD is similar. So basically, you just look at the image once. So how it did it is like you just like partition the image into many pieces. So you assume that there's an object there. So therefore, like for each of this block, I'm going to trying to detect, see if I can detect an object. And because like the object can have like different shape and size and dimension, right? So therefore, like for each of the block here, we'll also try differently um, propose dimension, propose how do they call it? I forgot, like proposal box or something. So then like you just try like different boxes and then see like if there's an object there. And for this of each of these box, I will try to like classify and also like try to like do a regression as well, because maybe I look at this box, there's a likely there's an object there, but the object like may not be exactly fall into this box here, or like it may be larger or smaller, or like slightly off. So we want to have some refinement of this box. So then we have another regression again. Um, and one thing like to mention is like uh, about YOLO, like YOLO and SSD, like this kind of like one stage approach, like typically is doing worse than the two-stage approach. And there's an interesting paper like trying to address that. They think that there's no particular reason why the one stage approach is worse. So what they believe in is like it's doing worse because the data like you use for training is imbalanced. If you have a two-stage approach, when you do classification, because you already have a vision proposal network, the input like to your classifier most likely will will contain an object. So, but on the other hand, when you do YOLO, like when you train like this, most of the input will be negative inputs, and most of the time you don't have any objects. So therefore, to address this kind of imbalance, what they propose is like uh, we need to like adjust the loss somehow. We want to make sure that like we don't have the loss that will be kind of like focus too much on the easy examples. So what they suggest is something like that. So if you think of the loss that typical people use is the cost entropy loss. I mean, if we show the cost entropy loss, we'll have like something like that. This is a cost entropy loss. It gives like significant, maybe not a lot, but still significant um, weight for the data for the sample, they're doing quite well already. Basically, like this is like the probability of the ground truth class here. So when this one is high, it's meaning that it's like actually easy things to do. So so therefore, like what they try is like, okay, let's change the shape of this loss a little bit. Just they adjust the equation a little bit to make it more kind of like skew to the lower value, lower probability here, so that it will give more emphasis on the more difficult samples. So and they show that like okay, uh, actually the paper like they is essentially like that introduced this like focal losses like also like they present the letter here they call it Watina lat also like by same group I guess I uh girls can also like coming here is her is like both of them are in the paper and they also use the feature pyramid network. They one of the power like as uh, the skeleton, and essentially like this is the main thing is I just using this focal loss, and they're doing quite well. Like compared with power, especially, it's competitive. Competitive even like compare with like uh kind of like those two stages approach. And if yeah yeah. Of course, like there, I don't know. There's a this is YOLO version 2. There are lots of version of YOLOs, version 3, version 4. And I don't know the number or numbers on top of my head though. So so this is like object detection and okay, maybe just quickly like wrap this up. So like mention like also like instant segmentation that is like we want to have like both like find the object like kind of find the object also like trying to find like the precise boundary of the object basically like just highlight all the pixels that contain the object so with the kind of like what we have like done and be doing like for the object detection then it won't be too difficult because like once we know where the object what we can do is like we can just put up another branch of the network to do semantic segmentation. So is okay. Yeah. So yeah, precisely this is just we do the classification already, right? So then we have this part here. Let's say we can do a uh, prediction for the mask, and that would be like just doing like semantic segmentation as we mentioned earlier. So I mean, this part of the lecture, you essentially just doing semantic segmentation. So and again, you can train end to end, and then like get very good results, and like this is a uh, mass CNN, and of course, you can also do post estimation as well, like for like now not in this case not for just one object from but for many objects because the post again is just you can consider this the parameters for the post is just um, yeah you can do regression for those parameters. Okay, so anyway, I guess this is good timing to end. So I guess yeah, if we'll talk about like visualization of neural network, I mean CNN next time. And if you guys don't have any questions, then I will just stop here. Then yeah,
Okay, maybe a quick question.
yes,
When we do like a regression task on top of a convolutional neural network,
yes.
um, what what does the end of that network look like? Do we need like fully connected layers? Or
Uh,
how do we get down to just like for in the case of like YOLO? How do we get down to just like the bounding box of the four?
Actually, one thing is that you can do is of course you can do fully connected layer, but the other thing is people now come and just do a so-called average pooling. So let's see. So yeah, I don't really have a slide that's good for that. But so okay, let's say this one here, right? Okay, let's say like this is like the second last layer before like fully connected layer. Of course, I can do a fully connected layer to do a regression, like to connect to this coefficient, like basically weighted sum of
Yes.
this guy. Um, but actually, by the way, like this also can, this is also can be just treated as a uh, so if I do a so-called FH pooling, I can just sum all of them together. So the difference is like whether I do the weighted sum. So of course I push the task to the earlier layer. Then if I do that, like this
I
lowest
see.
parameter now. Yeah,
Yes.
yeah. So but on top of my head, I'm not sure like how big the difference in performance though. Like you may want to
But
take.
there's different ways you're saying to
Yeah, you can definitely just do it like without convolution. Just do a weighted, just do a sum basically.
so you can still you don't need fully connected layers. You can just do a fully
Yeah,
convolutional network
yeah.
and get the regression. Okay, thank you.
Yes. So okay, I guess if no other questions, I will see you guys Thursday then.
Thank you, Professor.
Yeah, thank you. Okay.